Now let us see the definition of residue. If Z is equal to Z naught is an isolated singularity of any type means actually it might be poles or removable singularity or essential singularity. Okay, so if it is of any type, then the coefficient of 1 by Z minus A in the Lorentz series expansion is called as residue. So here what do you mean by the coefficient of 1 by Z minus A? In the Lorentz series expansion, it contains both positive power of Z as well as negative power of Z. In that negative power of Z, we have to consider the term 1 by Z minus A. So the coefficient of this term is called the residue of the given function. So here already we know the formula based on the Lorentz series expansion, how we are defining an and bn. So likewise here b1 is equal to b1 is nothing but coefficient of 1 by z minus a. So that here b1 is defined as 1 by 2 pi I into integral over c f of z dz. So that this is called as residue of the function f of z at z equal to 0. So while doing the problem, let us see how to find the residue or how to evaluate the residue. So while evaluating the residue for a given function, there are two methods. One is called as simple pole, that is how to calculate the residue for a simple pole, and how to calculate the residue for a pole of order m. So whenever if we want to calculate the residue for a simple pole, so what do you mean by simple pole? Simple pole means it is a pole of order 1 is called a simple pole. So the formula is residue of f of z at z equal to z naught is given by limit z tends to z naught, z minus z naught into f of z. So this is a formula to calculate the residue for a simple pole. Similarly, for pole of order m, what is the formula is limit z tends to z naught 1 by m minus 1 factorial into d m minus 1 by dz m minus 1 means m minus 1th derivative of z minus z naught whole power m into f of z. F of z is the function given in the problem. So for that function, how to calculate the residue for the poles. Okay. So whenever if the pole is a simple pole, we have to apply the first formula, and when it is a pole of order m, we have to apply the second formula. So now let us see simple example how to calculate the residue at their poles. So first let us take the first question. F of z is equal to z by z square plus 1. So before calculating the residue, first we have to identify the poles. So here to identify the poles, that is to identify the singular point, as I told you, we have to equate the denominator to 0. Suppose if we consider the function here for the first question, the function is z by z square plus 1. So to find out the singular point, we have to equate the denominator to 0. So the denominator is z square plus 1 is equal to 0. So here let us factorize this. Z square plus 1 can be written as z plus I into z minus I. Why it is like this? So z square plus 1 equal to 0 means z square is equal to minus 1. So if we take square root on both sides, z is equal to plus or minus root of minus 1. But root of minus 1 is nothing but I. So plus or minus I. So plus I is one of the root, minus I is one of the root. So while writing it as a factorization form, we can write z square plus 1 equal to 0 as z plus I into z minus I is equal to 0. So finally we can conclude that z is equal to I and minus I are called as singular points, or we can call it as poles, or we can call it as simple poles. Why we are calling it as simple poles is here both are of power 1. That is, this can be written as z divided by z plus I into z minus I. Here both are having power 1, which means that the factor occurs only one time, so that it is called as simple poles. So whenever it is a simple pole, what is the formula to calculate the residue? We have to recall the formula. So what is the formula to calculate the residue for the function having simple pole? So here the simple pole, let us take the pole as a, suppose. Then the formula is limit z tends to a, z minus a into f of z. Okay, so this is a formula to calculate the residue at its simple pole. So now here we are going to calculate residue for the function f of z at z is equal to I. So it will be limit z tends to I. Here z minus I into the function is z by z plus I into z minus I. That is, instead of z square plus 1, we can write it in the factorized form. If we write it in the factorized form, then we can easily cancel this term. So that here limit z tends to I will be getting z divided by z plus I. So now here we have to substitute the limit z equal to I. So which is equal to I divided by 2I. So here I get cancelled, that is I plus I is 2I denominator. So the answer is 1 by 2. Clear? Next is to calculate the residue for the another pole. So f of z at z is equal to minus I we want to evaluate. So limit z tends to minus I. According to the formula, it should be z minus of minus I, means we have to write it as z plus I, into the function is z by z square plus 1. Again z square plus 1 can be written as z plus I into z minus I. So here we can cancel z plus I, z plus I. So the remaining term we have to apply the limit as minus I, which means that z divided by z minus I. So if we put numerator will be minus I, denominator minus I is minus 2I. So the answer will be 1 by 2 again. So this is the way to calculate the residue for a given function, and if it is a simple pole we have to use this particular formula. Next problem is second problem is given as f of z is equal to e to the power z divided by z minus 1 whole cube. This is the second question given. So here first let us consider the pole. So here z minus 1 is the denominator term. If we equate it to 0, z is equal to 1 is the pole, but it is of order 3. So is a pole of order 3. So because it is repeated 3 times, so we have to write z equal to 1 is a pole of order 3. So now we have to remember the formula to calculate the residue of f of z at z equal to a, and it is of order m. If it is a pole of order m, then the formula is limit z tends to a 1 by m minus 1 factorial dm minus 1 by dz power m minus 1 into z minus a whole to the power m into f of z. So this is what we have to remember. So this is the formula if it is a pole of order 3. Now let us see pole of order 3, which is given here. Residue of f of z at z is equal to 1. It is a pole of order 3. So here we have to replace m is equal to 3, which gives you 1 by 2 factorial, and here d square by dz square of, here it is z minus 1 whole cube because m takes the value 3 here, into f of z. F of z is what? E power z divided by z minus 1 whole cube. So here what happened? This and this get cancelled. So it's enough to differentiate the term, that is d square by dz square of e power z. So differentiation of e power z twice will give you the same term e power z, because differentiation of e power z is e power z. So again, if we differentiate also, we will be getting e power z. So that the answer will be limit z tends to 1. 1 by 2 factorial is 2 into 2 times differentiation of e power z is e power z. So which means that here the finally the answer is e divided by 2. Why it is e divided by 2? If we put the limit z tends to 1, here it becomes e to the power 1, that is e divided by 2. So this is the answer, and this is a residue for the function e to the power z by z minus 1 whole cube. So here first we have to check whatever the problem given or the function given. They ask you to calculate the residue. First we have to identify the poles. So if it is a pole, if it is a simple pole, we have to use the first formula, and if it is a pole of order m, we have to use the second formula.